Welcome to the world of digital electronics, where logic meets innovation to power modern technology. In digital systems, many circuits do not just depend on current inputs, they also depend on what happened previously. To model this kind of behavior, we use something called a finite state machine, or FSM. A finite state machine is a mathematical model used to describe a system that can be in one of a limited number of states at any given time. The system transitions from one state to another based on inputs or specific events. Now let's look at the core components of an FSM. First, states. A state represents the current condition or mode of operation of the system. Second, inputs or events. These are signals that trigger the system to change from one state to another. Third, transitions. A transition is the movement from one state to the next state based on the input condition. Fourth, the initial state. This is the starting point of the system when it is powered on or reset. Finally, the output. The output depends on the type of FSM design being used, such as Moore machines or Mealy machines, which we will explore in the next sections. Finite state machines are widely used in digital design applications such as traffic light controllers, communication protocols, sequence detectors, and processor control units. Understanding FSMs is fundamental for designing sequential logic systems in ASICs, FPGAs, and embedded hardware. To understand a finite state machine in a simple way, think about a traffic light. A traffic light does not behave randomly. It moves through a fixed set of states in a specific order. The first state is red. The second state is green. The third state is yellow. So at any given moment, the system is in only one state. Now, how does it move from one state to another? The transitions happen based on a timing event. After some time, the traffic light changes from red to green. Then, after another time interval, it changes from green to yellow. And then, after the next timing interval, it changes from yellow back to red. This cycle continues again and again. That is why this is called a finite state machine. The system has a finite number of states, and it changes between them in an ordered and predictable way. This is one of the easiest real-life examples of sequential logic, where the present behavior depends on the current state of the system. In digital electronics, finite state machines are widely used to control systems that operate in a sequence of states. You will find FSMs in many real-world digital designs. For example, they are used in sequence detectors, where the system monitors an incoming stream of bits and detects specific patterns. They are also used in traffic light controllers, where the lights change from red to green to yellow in a predefined order. Another common application is vending machines, where the machine changes states depending on the coins inserted and the product selected. FSMs are also essential in protocol controllers, which manage communication between digital devices. And inside processors, FSMs are used in CPU control units to coordinate the execution of instructions step by step. Now let's look at how a hardware FSM is actually built. A hardware FSM typically uses flip-flops or registers to store the current state of the system. Then, combinational logic is used to determine what the next state should be based on the current state and inputs. Finally, output logic generates the required outputs for the system. Together, these components form the basic hardware structure used to implement finite state machines in digital circuits. Finite state machines are mainly classified into two types, the Moore machine and the Mealy machine. Let us start with the Moore machine. In a Moore machine, the output depends only on the present state. That means once the state is known, the output is fixed. It does not change immediately with the input unless the state itself changes. Now let us look at the Mealy machine. In a Mealy machine, the output depends on both the present state and the current input. So here, the output can change whenever the input changes, even if the state remains the same. This is the key difference between the two. In the block diagrams shown here, notice that in the Moore machine, the output logic is driven only by the state register. But in the Mealy machine, the output logic receives information from both the state register and the input. Because of this, Moore machines usually provide more stable outputs, while Mealy machines often respond faster and may require fewer states. So in simple words, Moore output depends only on state, whereas Mealy output depends on state plus input. This distinction is very important when designing sequential circuits in digital electronics. Now let us understand a Moore FSM design example by using a 101 sequence detector. The goal of this FSM is to detect the binary pattern 101 in a serial input stream. In this design, we use 4 states: S0, S1, S2, and S3. State S0 is the initial state where no part of the sequence has been detected yet. If the input is 0, the machine stays in S0. If the input is 1, it moves to S1, which means the first bit of the sequence has been detected. From S1, if the next input is 0, the machine moves to S2. This means the pattern 10 has now been detected. If the input is 1, it stays in S1, because the machine still has a possible start of the sequence. From S2, if the input is 0, the machine goes back to S0, because the expected pattern is broken. If the input is 1, it moves to S3, which means the full sequence 101 has been detected. Now from S3, if the next input is 0, the machine moves to S2. If the input is 1, it goes to S1. This allows the FSM to continue checking for overlapping patterns. Now look at the output behavior. In a Moore FSM, the output depends only on the present state. That means the output is state-based. So for this example, in S0, output Z equals 0. In S1, output Z equals 0. In S2, output Z equals 0. And only in S3, output Z equals 1. So whenever the FSM reaches S3, we know that the sequence 101 has been detected. This is the key property of a Moore machine. Output depends only on state, not directly on the input. One important correction for this slide: the green note at the bottom says output depends on present state plus input. That statement is for a Mealy FSM, not for a Moore FSM. For this slide, it should say output depends on present state, ... Now let us look at the Mealy machine using the same 101 sequence detector example. In a Mealy FSM, the output depends on both the present state and the current input. This is the key difference compared to a Moore machine. For this design, we use 3 states: S0, S1, and S2. S0 is the starting state, where no match has been found yet. When the input is 1, the machine moves from S0 to S1, and the output remains 0 from S1. If the next input is 0, the machine moves to S2, and again the output is 0. At this point, the partial sequence 1, 0 has been detected. Now, from S2, if the next input is 1, the machine moves to S1, and the output becomes 1. That means the full sequence 101 has been detected. So step by step, the input stream goes like this. Start in S0, read 1 and move to S1, output 0. Read 0 and move to S2, output 0. Read 1 and move to S1, output 1. That is how the sequence 101 is detected in a Mealy machine. Now, compare this with the Moore FSM for the same sequence. A Moore FSM usually needs 4 states, while a Mealy FSM usually needs only 3 states. Also, the Mealy output comes faster because it is generated directly from the present state and the input. In contrast, the more output is usually more stable because it depends only on the state. So the main idea is this. Mealy machines respond faster and often use fewer states, while Moore machines are simpler and more stable in output behavior. There is one correction needed in this slide diagram. The lower right state is labeled S2 with Z equals 1, but in a Mealy FSM, output should be shown on the transitions, not inside a state as a fixed state output. So for a cleaner Mealy diagram, the states should remain S0, S1, and S2, and labels like X equals 1, Z equals 1 should appear only on the arrows.